Welcome to the lecture for Chapter 5 on Newton's third law of motion. This is our last chapter where we're going to cover Newton's laws because this is Newton's third law and Newton has 3 laws of motion. Alright, so let's get into the content. Alright, so we're going to talk about forces and interactions, kind of defining what they are. We're going to discuss Newton's third law, give it a definition, see where it applies. We're going to talk about how the third law can be understood with vectors to get a little bit more practice with the concept of vectors, these quantities that have magnitude and direction. And then finally, we're going to see a summary of Newton's 3 laws of motion all together. So we're going to bring together all the chapters we've seen on Newton's 3 laws, which have been, this chapter, chapter 5, chapter 4, and then also chapter 2, because we had a little interlude there where we spent some time to clarify velocity and acceleration. All right, so what are forces and interactions? So an interaction is between one thing and another. So you can't interact with yourself in the context of Newton's third law. There has to be 2 objects for an interaction. Okay? And it requires a pair of forces acting on the 2 objects. And one force acts on one object and the other force acts on the other object. All right? So you can't have both forces acting on one of the objects because then the other object might as well not be there, and now you don't have a force and interaction. It's important to clarify that. So 2 forces, 2 objects, 1 force per object. All right, example, interaction of hand and a wall, pushing on each other. It's a force pair. You push on the wall pushes on you. Okay? Now, as someone that teaches physics, that seems perfectly natural to me to talk about the floor pushing back, or the chair pushing back, or the wall pushing back, or if I pull on Earth, or rather if Earth pulls on me, then I pull on Earth, all these sort of things I take for granted, but they seem strange at first pass. Think about it maybe at the atomic level, right? Kind of understanding that ultimately, microscopically, there must be some sort of interaction going on, and ultimately that's what leads to the macroscopic, everyday scale of the idea that if you push on something, it pushes back. Okay? So Newton's third law of motion says, whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. For every action, there is an equal and opposite reaction. Opposite in direction. Okay? That's what the opposite means. Okay? So there is a directionality that's inherent in the definition of Newton's third law. Case in point, looking at this picture, right? The hammer exerts a force down, the peg exerts a force up, the magnitude of the forces are the same in a story, okay? Now, does that mean that the net force on either of the objects is 0? Absolutely not. Absolutely not. And you can clearly see there's only one force acting on the peg and there's only one force acting on the hammer. So both of them have a non-zero net force, so they're both going to experience acceleration. So we're not saying that everything cancels out. We're just saying that a force pair is created every time 2 objects interact with each other. Okay? Soccer player kicks a ball with a 1,500 Newton force. The ball exerts a reaction force against the player's foot of what? Right, so imagine that. Player comes along, kicks the ball. Right? Obviously, the ball moves much more than the player does. Does that mean that the ball is experiencing a much larger force than the player? Think about it. No. They have to be equal in magnitude. Okay? The reason that the ball accelerates so much and the player doesn't accelerate backwards very much at all, it's not like the player recoils from the kick, is because the mass of the player is so much greater than the mass of the ball. And think Newton's third law. Think F equals ma. So if F is equal, if it's 1,500 newtons for both the player and the ball, but the mass of the ball is much smaller than the mass of the player, then clearly the acceleration of the ball will be larger, much larger than the acceleration of the player. Okay, and we're going to see examples of that again. Okay, so Newton's third law of motion, another way to think about it, action and reaction forces. One force is called the action force, the other force is called the reaction force. It's a little arbitrary. Okay, maybe it's just kind of like just your perspective. Okay, they're all co-pairs of a single interaction. Okay, so that's the thing. That's the inherent nature of interactions. This applies to particles as well. If we're talking about physics at the particle level, there's co-pairs of every interaction between electrons and protons and leptons and muons and all these things. There's always going to be these reaction pairs. Neither force exists without the other. It's simply impossible. Okay? There's no asymmetry in that regard in physics. They're equal in strength and opposite in direction, and they always act on different objects. Okay? As I said before. And the reason is because there's certain cases where you can convince yourself that there's a force pair on the same object. You can be like, oh, well, there's tension on this rope, and there's tension at the bottom, and there's tension at the top, and they're equal in magnitude, and they're opposite in direction, so maybe those two tensions, the tension at the top of the rope and the tension at the bottom of the rope, that forms a force pair, right? You know, equal in magnitude, opposite in direction? No, because they both act on the rope. You know, so that's why I make a big deal about this idea of different, because there's pitfalls. There's opportunities to see something that looks like a force pair, but remember it's not, because it's acting on the same object. Okay? It is, so a re-expression of Newton's third law is the following. To every action, there is always an opposed equal reaction. Okay? And that's kind of the way that maybe you see it more poetically. For every action, okay? Example. Tires of a car push against the road while the road pushes the tires forward. All right? And that's made possible by friction. Okay? That's how we can have a horizontal force of the tires, right? There's this friction force. It's being applied. The tire pushes on the road pushes back. That actually creates a thrust on the car. Okay? Forward motion. Okay? So a simple rule to identify action and reaction. Identify the interaction. One thing interacts with the other. Action. Object A exerts a force on object B. Reaction. Object B exerts a force on object A. Example. Rocket. Okay, so the action, the rocket, exerts a force on the gas. Okay. Reaction. The gas exerts a force on the rocket. See, the rocket pushes on the gas pushes on the rocket. Sometimes you might say it pushes back on the rocket, right? Just to maybe call more attention that it's the reaction. But that's the idea, okay? And it's a very fascinating force pair, isn't it, right? Think about the idea that it's actually the rocket pushing on the gas, and the gas, they're just a gas. Gases don't seem like they can exert a lot of force. But of course they have to. Newton's third law says they do. And otherwise, how would rockets fly? All right? They'd equal and opposite force. The gas pushes back on the rocket just as much as the rocket pushes on the gas. And, foreshadowing things to come, we're going to come back to this idea and it turns out a perfectly other valid way of thinking about Newton's third law is to think about momentum. It's right into it. And so I'll remind you of that when we get to the chapter on momentum, because it's so important to see that it's really a choice of how you want to conceptualize it. What makes more sense, what's better suited to this particular situation, a particular understanding, okay? And not to get lost in the subtleties of being like, oh, these are two very similar things, which do I choose? It's just, but you can choose either. All right? So it's more like you have these tools that we're building up. We'll have a better tool belt as we proceed in the class. So, question. When you step off a curb, the earth pulls you downwards. Clearly, right? That's how you fall. What is the reaction to this force? Make sure you get this one. Okay? You all got an answer? You pull up on the earth. You pull on the earth every single time. If I jump in the air right now, while I'm airborne, I'm not interacting with the floor anymore. And so that means that the force that's pulling me down is exactly equal to the force that I'm pulling the entire earth up towards me. Now here's the thing. The earth is 10 to the 24 kilograms. So the acceleration that the earth is going to experience from my couple hundred Newton force is so small that it is practically immeasurable. And by practically, I mean really by any stretch of the imagination, it's immeasurable. All right. So when you step off a curb, earth pulls you downwards and you pull earth upward. Why do you not sense the earth moving upward towards you? Well, it's just very little. The acceleration is just basically, 0 point and then 20 zeros or 21 zeros or something, and then a 1 or a 2 or something. And it's those 22 zeros after the decimal point that make that an imperceptible acceleration. Okay? But if a massive enough thing jumped, then there would be a perceptible acceleration. Okay? But it'd have to be pretty massive, wouldn't it? Right? You could think of a case in point. What if you had a huge extinction event asteroid coming in and crashing with Earth? Well, then what's actually going to happen as the asteroid comes down to the surface, it would pull Earth a little bit towards it, a perceptible amount. Okay, although we'd probably be more concerned about other things than the small but measurable acceleration of the Earth towards the asteroid moments before collision. Okay, so moving on. So Newton's third law, action and reaction on different masses. I've already hinted at this, okay? So here's a good example. Consider a cannon firing a cannonball. So both the cannon and the cannonball experience the same force. We know that they must share the same force because the firing of the cannonball is a perfect example of a force pair. Okay, there's an action and then reaction. The cannon pushes on the cannonball pushes back on the cannon. All right, but here's the thing. The cannonball has a small mass, as indicated by a small font on the M. The cannon has a large mass, as indicated by the large font. That means the cannon experiences a small recoil acceleration. So it gets kicked back, but not nearly as much as the large forward acceleration of the cannonball. Okay? And the bullet points below reiterate what I've said. So when a cannon is fired, the acceleration of the cannon and cannonball are different because, you should be able to find the right answer here, simply because the masses are different. Okay? The forces are the same, but since the masses are different, Newton's second law tells us the accelerations must be different. So you see how the two laws, Newton's second and third law, really work well together to describe a lot of situations very fully. Now, not to say Newton's first law isn't very important too. We saw plenty of examples talking about equilibrium, being like, of course it's constant velocity because the net force is zero. So they all work in tandem. But we'll call attention to that again in a moment. Consider a high-speed bus colliding head-on with a flying bug. The force of impact splatters the unfortunate bug over the windshield. Which is greater, the force on the bug or the force on the bus? We have a tiny little bug, right? Just gets splattered on the bus. It's just like it just gets obliterated by the bus, and the bus just continues on its way. But we know they're the same. It's the same force. Same exact force. All right? It's just the fact that the bug experiences such a huge acceleration, while the bus almost experiences no acceleration because of the collision with the bug, that acceleration is so great that the body cannot withstand it. And it's simply the inertia of the internal organs, or everything inside the exoskeleton of the bug, the fluids, the guts inside that exoskeleton of that bug have inertia, and the exoskeleton can't hold them together, and so they just go off in all directions, basically turning into a complete fluid. Okay? So have you ever heard the phrase, it's not the fall that kills you, it's the sudden stop at the end? Well, case in point, right? Because when you hit the ground, you have two very different masses, you and the earth. Think about who's accelerating more. You are from a fall, and that's, hopefully it's not, we're not literally talking about you falling to your death, but as so it's the sudden acceleration at the end that at least could hurt you. Okay? So, two people of equal masses on slippery ice push off from each other. Will both move at the same speed in opposite directions. Equal masses. So what do you think? So we got an idea about unequal masses, but can we be confident that there's a result if they have equal masses? Think about it. Think about Newton's second law. Think about the fact they have to experience the same force. Absolutely, right? Because in this, so we basically have force action equals force reaction. And then we have MA equals MA from Newton's second law. M is the same for both of them because they're equal mass. So we could then just cancel. We divide both sides by M, which tells us that A equals A. They have to have the same acceleration. If they both have the same acceleration, then they must both have the same speed at any moment. So, say when we say the same speed, well, I guess we're saying, 1 second later or 1/2 of a second later after they've started moving really, then they'd have to have the same speed because they have the same acceleration, same amount of elapsed time in their motion. Okay? All right, so now we're going to have some fun defining a system because it's going to be a sticking point. I want to make sure we really understand what we mean by a system. All right, let's do it. Consider a single enclosed orange. Okay? So, we apply an external force, which causes the orange to accelerate in accord with Newton's second law. We see here the action force, the red vector, right? Because certainly when we talked about free fall, we just considered this is like free fall, right? We don't care about the outside world. We just have the orange, and we note that there's one force acting on it, thus it's accelerating. Okay, one force, thus acceleration. Okay, just like when you're in free fall, you have one force, that's your accelerating. Okay, all right. But let's look. Let's zoom out. Let's consider the other half of that force. Because in the free fall case, the skydiver, for example, the other half of that force was Earth. Okay? Many practical times we don't care about that. But if it's not Earth, if it's something smaller, maybe we do care about it. So, in this case, it's an apple. Okay? It's an anthropomorphic apple that is pulling our orange in the cart. Okay? So now, the orange and the apple pulling it. The action and reaction do not cancel because they act on different objects. All right? So the orange can still accelerate because it's still only experiencing one force. I mentioned that in the previous slide. Okay? Likewise, right? The apple is only experiencing a single external force, so it could accelerate too, right? Absolutely. Okay, looks good. Now, let's consider the system to include the apple and the orange. Okay? So now we're not asking if the orange, because here, to go back, here we're saying that the orange is accelerating relative to the outside world. That's absolutely true. But now, we're asking if the orange-apple system is accelerating relative to itself, right? Because now we have two forces, okay? The apple is no longer external to the system. The force pair is internal to the system, which doesn't cause acceleration. Because now we're saying, does the orange accelerate relative to the apple? No. No, it does not. Okay? Because this system has two forces acting on it. We know they're equal in magnitude and opposite in direction, these two forces here. Thus, there cannot be acceleration between the orange and the apple. Right? Okay. Okay, so there's no acceleration of that system. All right. But here's the thing. Now let's consider that same system, but now let's actually compare it to the external world. Because here, this was an entirely interior view. We were only looking at the orange and apple and saying that they're not accelerating relative to each other. So we kind of took our attention away from everything outside of the dotted line. But let's go back to it. Okay? So here's the same system, the one that's not accelerating relative to itself. All right? But with the external force of friction. Because otherwise, how's the apple moving, after all? Right? Okay, friction between the apple's feet and the floor. The external friction force of the floor accelerates the system. All right? So now we have that the orange is not accelerating relative to the apple, but the apple-orange system is accelerating relative to the ground. Okay? We have an F equals ma. F net. Because here the net force is not zero. Okay? So that apple-orange system will move with constant speed if what? How could we get rid of that acceleration, in other words? Let's take it one step further. Okay? How could we get rid of the acceleration of the apple-orange system? Well, simply, a force equal and opposite to the friction force occurs. All right? Because the friction force is the apple pushing on the ground and the ground pushing back. Okay? It's propelling the apple forward. But what if there was a friction force of the wheel that was equal in magnitude, opposite direction, that was slowing the cart down? Now there's two external forces acting on the apple-orange system, and they sum to zero. F net is zero. And the system could be in dynamic equilibrium, so it could still be moving, but it would not be accelerating. Or one could be slightly bigger than the other, and it could be either slowing down or speeding up. But the point is, you want to have an understanding of what we mean by systems. And I really want to make sure, because you probably at some point were like, well, wait. And that's what you want to go back and have that, wait, really? Does that make sense? And have it make sense. Okay? Ask me about it if you need to. All right. So consider the flight of a helicopter. When lift is greater than the helicopter's weight, the helicopter does what? All right. Think about it for a minute. Pause if you need to. Moves upward. Okay? We have an F net that's greater than zero. Okay? If F net is vertical. All right? Make sense? A bird flies by doing what? How does a bird fly? This is flapping motion, by the way. How does a bird with flapping, not gliding. Gliding has a lot of the same principles, but it's better to think about it in terms of fluid. If we're just thinking about Newton's third law and flapping motion, pushing air in each case, gave it away, you push the air down and the air pushes back up. All right? So a bird flaps to stay up in the air, stay in flight. Slightly tilted wings of an airplane do what? Here you go, right? Air rushing under the wing in a certain direction. Bet you can guess. The oncoming air is pushed downwards. Since the wing pushes the air down, the air must push back up on the wing with an equal and opposite force. There you go. That's your lift force. Pretty cool, huh? Okay. So compared with a lightweight glider, a heavy glider would have to push air, right? Because it's the thing, like, think about the idea, you have to have equilibrium in the vertical direction for something to maintain steady flight. So that means it would probably have to, push force down with a greater force, so push air down with a greater force. Okay, so more air, right? Different design of wings, or maybe it just needs a greater velocity in order to stay in the air, so it can't glide at very low velocity because it's just not enough air. All right, cool stuff, right? Food for thought. All right, so back to vectors. We've already seen this before. This is a review about vector components. I won't go over it, but if you kind of want to have a review right here in these slides, it can be helpful. All right, so let's consider Nellie Newton, one of our protagonists in our book. She pulls on a sled as shown. Which component of the force is greater? Well, look at them. Look at their magnitudes. All right, the horizontal one. Clearly, it's a longer vector. All right, so which two other forces not shown act on the sled? mg and the normal force. Okay, so there would be an mg force and a normal force, like so. Okay, N for normal. Normal is the support force of the ground, but the term we usually use is normal force. It's not because it's such a typical force, but normal actually means perpendicular. And so it's a force perpendicular to flat ground, okay? Or tilted ground for that matter. It's the normal force, all right? So two forces act on the block of ice. As the ramp is raised, which force remains constant? As the ramp is raised, how does the magnitude of N, that's the normal force, change? So you can either write it as N, F sub N like I did, to really call tension as a force, or you can just write it as uppercase N. Both are the normal force. Just two notations for the same thing. When the ramp is raised to 90 degrees, like here, what is the net force on the block? We can see, right? Look what happens. There, the answer isn't a quick check, is rather just kind of a demonstration here. When the ground is totally flat, the normal force equals the gravitational force. When the ground becomes tilted, now we see that the normal force is only equal to one component of the gravitational force. All right, see the shorter side of the triangle? All right, here's a right triangle. And so this vector here is equal to the normal force. So now the normal force has gotten smaller because mg has not changed. Remember, mg is independent of the tilt of the ground here. And if we make the ground even more tilted, mg is still unchanged, but now we have an even smaller component of the gravitational force, right? So now we call this FGY, y for vertical, and now FGY equals N. But see, FGY is much smaller than it was before, because here, mg was equal to FGY. It was the entire gravitational force mg was vertical. Now, only a small amount of it is vertical. And you might say, wait, what do you mean by vertical? Well, I mean vertical relative to the surface, right? This is a coordinate system that looks like this. Okay? This is the y direction, this is the x direction. So it's a coordinate system that's locked to the slope rather than locked to Earth. And then when the slope is, just a straight up wall, when the slope is a straight up wall, well, in this case, the net force is just mg. There is no normal force anymore. The wall might as well not even be there. It's just free fall, right? So can you see that N and mg are equal and opposite, right? That's an A. Absolutely, because that's the level ground. Can you see that N is less on the incline? Yep, just like we talked about. Now it's only equal to a component of mg. Can you see that the resultant N and mg is the force propelling Nellie down the hill? And can you see which component of mg is equal and opposite to N? Yep, it's this component right here. Okay, what I called the vertical component. This component right here, this is the one that causes acceleration. Now, if there's friction, there might be another force going in this direction, but if there's not, then the only force is this horizontal component of the gravitational force, and that's the one that actually accelerates Nelly. All right? So quick summary of Newton's three laws. Newton's first law of motion, the law of inertia. An object at rest tends to remain at rest. An object in motion tends to remain in motion at constant speed along a straight line. Remember, turning is acceleration. Newton's second law of motion, the law of acceleration. When a net force acts on an object, the object will accelerate. The acceleration is directly proportional to the force, the net force, and inversely proportional to the mass. And finally, Newton's third law of motion, the law of action and reaction. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. Those three laws completely describe motion. That's all we need to describe motion. We don't know where forces are coming from, so we have other laws to talk about the origins of forces. We need other laws to describe other phenomenon, like conservations of certain things, like momentum and energy. We need laws for things that are very large or very fast. These are modern laws of relativity and gravity and quantum mechanics. But I can't stress the elegance and importance of that these three laws describe every bit of motion. Okay? All right, so that concludes Chapter 5. Thank you for watching this video, and stay tuned to more lectures next week.